Question number 16. It's something a very beautiful one. At a glance, it seems that you need to memorize the value, but if you see carefully, the options have been very sensibly placed. We need to compare the resistivity of mercury, tungsten, aluminum and copper. Now, one fact is known that copper and aluminum, at least this much that's expected to know from all of you, that copper has lesser resistivity than that of aluminum. And if you know with this, you can just juggle around the option and you would get the correct one. I'll just show you how. Let's go by elimination. Now, if you go with option number 4, you could see it says that tungsten has a resistivity less than that of aluminum. Now, that doesn't make sense. So, of course, option number 4 would be ruled out. Option number 2, let's see. Now, option number 2 says copper has a resistivity higher than that of aluminum. So, this also does not make sense. Option number 3, if you see, it says that mercury has a resistivity lesser than that of aluminum. Now, that also does not make a sense because we know aluminum and copper, they are one of the good conductors. So, here you can see, because you know aluminum and copper, they are one of the best conductors. And on top of that, copper having a better conductivity than that of aluminum. So, obviously, option number 1 would be remaining and that would be the correct option. By the way, for your information, if I just give you the value, the resistivity part, if I see, the mercury has the highest resistivity, then comes tungsten, then comes aluminum, then comes copper. So, that would be the correct order of their resistivity. Now, let's go for question number 17. Question number 17, now this is from the collision part where conservation principles need to be applied. Now, let us see what it says. There is a particle of mass m with an initial velocity u I cap and that collides perfectly elastically. So, that has been given here. So, here I'll just try to show in terms of figure. Now, let's even write the value as well. It says that there is a particle of mass m moving in a direction in the positive x-axis. And the collision is perfectly elastic. The second member is 3m and initially 3m is at rest. Now, this is the story before collision. Now, let's see what happens after collision. After collision, it says the particle m, it moves with a velocity vj cap after collision. So, it's something like this. Here is the particle of mass m and that moves with a velocity vj cap. So, let me even write here. So, this is the velocity which is v. Now, we need to calculate the value of v. So, that is the specific question, that what would be the value of v. Now, here there is a second particle which is 3m. Now, just by seeing the sense of linear momentum conservation, if you see the initial momentum is along x, one of the final momenta is along y direction. So, quite obviously, the remaining one you can easily see the direction part can be guessed out, that would be in this direction. And let me call this as v dash. So, in doing so, what happens is that its one y component will cancel this because the initial y component is 0 and the x component will maintain the momentum along x direction. Now, let's try to see. There are two unknowns specifically, one is v, other is v dash, because v dash is an unknown and v that we have to calculate. So, we require two equations and let's generate the two equations. The first thing is, it's a collision. So, quite obviously, linear momentum would be conserved. And if I see the linear momentum, the initial is mu I cap will be equals to mv j cap and plus 3m v dash. Let me just give it in a vectorial way. Let me not go it in terms of I cap and j cap. Now, the second equation, where are we going to generate the second equation? Remember, the collision is elastic. And if it is elastic, the kinetic energy has to be conserved. So half mu square. The initial kinetic energy of 3m is 0. And there 1/2 mv square plus 1/2 3m v dash square. So that's how we have equated the initial and final kinetic energy. Now, one thing what you can do is that, the first equation you can modify as per the requirement. Now, if you just see the first equation, what is it going to be? You can simply write in this way, mu I cap minus of mv j cap will be equals to 3m v dash, isn't it? Now, let's try to take the magnitude on both sides. So, to take the magnitude, let's have the cancellation as well. So, this is going to be root of u square plus of v square, and that of course is going to be 3v dash. So, all done. So, this you call it as equation number 1, this you call it as equation number 2, you solve it, not a difficult one at all. You would get the value of v as u by root 2. So, here goes option number 4, that is the correct one. Let's go for the next. And here, question number 18, let's see. This is from optics. The question is a fundamental one, but the scalings are such that you need to pay attention to the minute detailings. If you just see the scale, that every scale moves by 2 centimeter. That is very clear, and it's a concave mirror, right? So now let's see. Let me just try to find out what are the parameters that we define for a mirror. Now this, of course, is going to be the pole. This is 16 centimeter, so radius will be 8 centimeter. That means here is the center. That's straightforward. After that, you could see if radius is 8 centimeter, focal length will be 4 centimeter. So this point will be focus, this point will be center of curvature. And where is the object? Between infinity and C. And if that is the case, the image will be between C and F, right? So now you can easily see that's a case of real, inverted and diminished image. So here option number 1, that is going to be the correct. So for question number 18, we have option number 1 as the correct option. All right, let's go for the next one, 19th question.